Hi, and welcome to this video on radioactive contamination, the radioactive waste that's produced by nuclear power stations and some hospitals and industries must be disposed of in such a way that the risk which it poses to humans and the environment is minimized. An object is said to be contaminated if it contains radioactive nuclei which will go on to decay and release ionizing radiation such as alpha particles, beta particles, and gamma rays. The way in which contaminated items are dealt with depends on a number of factors such as the amount of contamination present, the type of radiation emitted, and the half-life of the radioactive substance present. In general, long half-life gamma emitters are the most difficult to deal with because they'll continue to emit highly penetrating gamma rays for many years to come. Let's look at a couple of examples. In this first one, we're looking at the fuel rods that are used in a nuclear power station. As you can see, in part A, we need to work out the fraction of uranium-238 which is remaining after a time of 9 billion years. So let's give it a go. You should know that a billion is 1,000 million. So that means that, in standard form, 9 billion years is equal to 9,000 times 10 to the power of 6, or 9 times 10 to the power of 9 years. Using the table then, we can see that 9 times 10 to the power of 9 years is equal to 2 half-lives for the uranium isotope. After this length of time, the fraction of the original uranium remaining is going to be equal to a half times a half, which gives a quarter. Have a look through part B now. As you can see, the half-life of the plutonium present is much shorter than 9 billion years. So the kind of answer you might want to write down would look something like this. Have a read through example 2 now, which is about 2 of the potentially hazardous isotopes which were emitted in the Chernobyl disaster. As you can see, iodine-131 has a half-life of just over a week, and cesium-137 a half-life of around 30 years. The correct answer for part A is iodine-131. Because its half-life is quite short, it decays quickly, and so will have emitted lots of beta particles in the days and weeks after the disaster. The answer for part B then is cesium-137. It's very unlikely that there'll be a single iodine-131 nucleus from the disaster remaining after this time, but the amount of cesium present will only have fallen to half of its initial level, meaning that it will continue to pose an ongoing health risk in the affected area. Irradiation is the process of exposing an object to ionizing radiation. When alpha particles, beta particles, or gamma rays pass through an object, they can transfer some or all of their energy to it, but they won't make it radioactive. To put this another way, an object will only undergo irradiation when it's within range of the radiation emitted by an alpha, beta, or gamma source. As soon as the object is moved away from the source, or a suitable absorber is placed between it and the source, it will no longer receive radiation from the source. Irradiation by alpha particles, beta particles, and gamma rays can't change the nuclei of the atoms that make up the object. Therefore, it can't decrease their stability. Although it can't make them radioactive, irradiation by alpha particles, beta particles, or gamma rays can still damage objects, however, including living things, which is why it's a good idea for us to minimize our exposure to ionizing radiation at all times. This is why your teacher holds radioactive sources for as little time as possible and uses tongs to do so. It's why radiographers stand behind leaded glass when carrying out X-rays, and why nuclear reactors are shielded by dense concrete, lead, and other absorbers. It's not all bad though. Irradiation can be really useful too. Gamma rays can be used to sterilize both foodstuffs and medical tools, for example. Alright, that brings us to the end of this video on radioactive contamination. Thanks for watching, and good luck.